I want to finish our section on max flow min cut and talk about applications of it. In particular, the homework for this week, homework 7, is all about applying max flow min cut. So if you're coming up with a solution that is not involving a max flow algorithm, then reconsider. So once you frame the problem in terms of max flow min cut, hopefully it'll be easy. And we'll talk about 3 examples today and how you make those arguments. Question?
That applies to all problems?
All 3 problems, yes. 4 problems. Yes. I would also like to ask if you have a problem with grading. So I apologize. The grading situation I'm not happy with. I don't know why. I've done my best to get enough TAs to get involved in this process, but I saw some of the comments. They're not very helpful. So if you have issues with grading, I'd like you to create a private issue in Piazza for me so that I can try to resolve it. And it's the best issue system I can have. So if you have some issues like that, I'd like to resolve them quickly. So after class, please start creating issues that I can resolve with Asif, the TA, quickly. There are solutions to homework 5 and 6. Please pick them up because you'll probably need them for the take-home exam. That's all I need to. I'll have office hours again tonight and tomorrow night, but right after class, I need to go on a trip. Or one of my research sponsors in Washington, D.C. So I won't be here after class, but I will post a Google Hangout link later tonight. Okay, so what was the general approach? What was I looking for? Basically, this is the idea of finding augmenting paths If there's one thing that you take away from this class in the max flow section, it's that these max flow problems are almost greedy algorithms. It's almost try to take the most flow you can. The only twist on it is keep this augmenting graph, keep this residual graph around so that you can undo some of the mistakes that you might have made. And so the major technique that we're talking about in this class is basically finding paths from the source to the sink in residual graphs. If you do it by Ford-Fulkerson, which is to say, take any path, you have some complexity measure. And if you do it with something slightly more sophisticated like Edmonds-Karp, then you can get some different type of running times there. When Ford-Fulkerson finishes, how do we know that the answer is correct? Because we can identify a cut associated with resulting flow such that the value of the flow is also the value of this cut. And by the max flow min cut theorem, this implies that F is a max. Right? So I hope that this is a similar pattern that we're using with this type of algorithm to other ones. Right? So Ford-Fulkerson, you initialize a flow to 0 and you just look for an augmenting path, and then for every path that you find the critical value, the bottleneck value on that path, and you augment the flow with that value along that path. The only difference with Edmonds-Karp is that you use a specific way to find that path. In particular, you use breadth first search. It's the difference between these two. And as we argued before, right, some edges are critical when they're, so for every path, some edge is critical, okay? And that critical edge is removed in the next augmenting graph, in the next residual graph. And based on that property, we can establish the following. I'm not going to go through these steps, but I'm going to say step I is so for every edge, if E is some edge between U and V, okay, at time I, suppose E becomes critical. Okay? So that's the first time it becomes critical. And then suppose K So the Edmonds-Karp argument is to say, if an edge E becomes critical at time I for the first time, and then the next time it becomes critical is time K, we're going to show some interesting property about that. So if we skip all the intermediate steps, which are these diagrams of how this process actually happens, we essentially come to the conclusion, which is that at time K, the distance of U from S is greater than the distance from U to S at time I by a constant 2. So between every time that an edge becomes critical, the first node of that edge becomes 2 edges farther from S. Okay? And so this immediately implies that edge E can become critical at most V over 2 times. Why is that? Oh, thank you so much. Thanks. So, those previous 3 slides, what they established is between time K and time I, the first time that this edge becomes critical and the second time it becomes critical, this node U becomes 2 units farther from the source. And so now I want to argue that this edge can only become critical V over 2 times, because after V over 2 times, the distance from S to U is going to be greater than V. Does everybody see? The first time, it gets 2 units farther. The second time, 2 more units. The third time, 2 more units. So after V over 2 steps, you'd be more than V units away from the source. So that means you can never be on a path from the source to the sink, because you'd be more than V units away, and simple paths can have at length at most V minus 1. Is there a nod? Does that make sense? Okay, good. So that's all we needed in order to get a running time, because this means that each edge becomes critical V over 2 times. They're only E edges. And so the number of times that we're going to have to find a critical path is EV over 2. The time to find a critical path is just breadth first search. Okay? And so the total time is going to be E squared V. So what did I want to say here? So these are all the augmenting path mechanisms. And these mechanisms are more modern techniques. They're push-relabel techniques. And you can actually show that you get, so in the first step, you see how this is E squared V, you can actually get E V squared, which is slightly better. And if you're even more clever, you can reduce this to a V cubed algorithm. Okay. Very good. So, applications of the max flow. This is why I think this algorithm is really critical. You can reduce a lot of interesting problems, as you'll see all of the homework problems, and the ones I present today to this problem of max flow. So the first problem is, I introduced it last class, it was bipartite matching. Right, so we have, let's say, 4 people here and 3 colleges, and we would like to assign students to colleges. So there are many ways for us to do this. Of course, one way is to do something like this, right? And so in this matching, 2 people matched. Okay? But clearly, we can do slightly better, or, well, it's not clear if this is better, since, as I mentioned, sending someone to Yale might actually be a disservice. But now, in this case, 3 people are matched. Okay? So what is the this is a framework for doing any sort of assignment type of problem, where you have left sides and right sides. People on the left need to be matched with people on the right. So for example, classes need to be assigned to classrooms. Or people who work in factories need to be assigned to jobs in factories. You'll see that the first problem, the gold Boolean face problem, also can be related to a bipartite matching problem. Okay, so what exactly is this bipartite matching problem? So we're going to be given a graph, and this time the graph is going to be expressed as, these are the nodes. Okay, bipartite means you can basically partition the graph into nodes on the left and nodes on the right, and the edges only connect elements from the left to elements to the right. Okay, so we're given a bipartite graph like this, and we need to find the largest So we're looking for a set of edges, the largest one, such that each vertex is incident to, at most, one edge in M. Okay, so if we go back to this example right here, notice that each person on the left only has one edge that's connected, at most, right? This guy doesn't have any, unfortunately. Probably will go to a startup and be very wealthy. And these colleges only have one student as well. Right? This is what a bipartite matching is. A set of edges in which each vertex in the original graph is incident to at most one of these edges. In other words, you assign each person on the left to at most one person on the right. Okay? So, okay, so here's an example of an input bipartite graph. How do we solve this problem? Yep.
Could you frame it as like a max flow from the left side to the right side?
That's right.
Take some supernode on the left that connects all the left ones and one on the right that's connected from all the right ones?
So we're going to add a source here and a sink right there, and we're going to connect like this. What do you think the capacities of the edge should be? 1. That's right. Every edge, we're going to put capacity 1. Okay? So the algorithm is going to be transform G into G prime, run max flow, output the middle edges with flow 1. This is the algorithm right here. So you take your input red graph, which was G right here, you turn it into this blue graph G prime. How much time does that take? Step 1. How much time does step 1 take? I gave you a red graph and you turned it into a blue graph. Yeah, it's going to take, you just have to add edges that correspond to each of the vertices. So it should basically take order v time, because you had to have that many edges. Now you're going to run max flow. We'll analyze this step in a little bit. And then you're going to scan all the edges and look for all the middle edges that basically have a flow of 1. And those are the edges you're going to output. Intuitive algorithm, right? Just add a source and a sink and call it max flow and we're done. The question is, why exactly does it work? And this is the trick to take away for your homework. You're going to have to prove something like the following. Okay, so why does this work? Oh. We need to show G has a maximal matching of size k if and only if G prime has a max flow of k. This is how you prove that it's correct. Okay? So how do we do it in the first direction? So G has a matching of size k, then G prime, so this is this direction. How can we show this? For each edge, right, so it has a matching M of size k. So for each edge in that matching, set the flow of that graph to be 1 in G prime. And then, so that's, right, then we're going to do 3 things here actually. We're going to set that. We're going to set the flow of S to X to be 1. And we're going to set the flow of Y to T to be 1. Okay? And now we need to verify that this is a matching. Verify that this is a flow. So, notice that the only way that a node gets, notice that the only way that a node on the left has any input flow is if this occurs. And if it has, in other words, if a node on the left, X, has incoming flow, then it's also going to have outgoing flow because it's going to have a flow from X to Y because of this step. Similarly, if a node on the right has incoming flow because this is true, then it'll have outgoing flow. So every node will satisfy the flow constraint. So the flow constraint is checked. Right? Every node in the graph, if it has any incoming flow, it also has outgoing flow of the same value. Capacity constraint? Why is the capacity constraint satisfied? Because the capacity in this graph was 1 for every edge, and we're only assigning flows of value 1, right? Okay? There's one other point about this flow constraint I'd like you to make yourself. So I argued that if there was incoming flow, then there was outgoing flow. What if there were two incoming, what if there was some node X that had incoming flow of 2 and outgoing flow of 2? What prevents that? Yeah?
Well, like then it wouldn't be a bipartite graph because for all your nodes on the left, all the incoming flow is always 1. For all your nodes on the right, the outgoing flow is always 1.
So that's basically right. We're starting with the matching. The way we're creating this flow is from a matching. So that means that for every edge that's in this matching, for every vertex that's in this matching, at most one edge is incident. So this procedure happens at most once for each node on the left and right. Okay? And of course, since the size of M is K, this implies that the outgoing flow from S is K, right? Which implies that the value of F is K. Yeah?
Can you show on that picture what M represents?
What M represents? Yeah. So how about, instead of on this example, so here, M is going to be the set, which is fish and UVA, cow and Harvard, and dog and Yale. So that's the set M. Today that projector is not working in this room. It'll be fixed by Friday, apparently.
Watch it explode.
Oh, you saw it explode?
It was awesome. It was a loud bang and magic smoke this morning.
Oh.
It is physically broken.
I'm sorry.
It waited a few seconds to die. Like after that, it was still soldiering on.
Nobody took a video of that. Oh. Now the question is, right, all three of them purchased on the same day, same company, same model, same use. So when are these going to explode? Okay. So this is the type of argument. This is half the argument to say if G has a matching of size K, then G prime has a flow of size K. A similar argument you'll make on your homework for all three of these problems. That's the first half. The second half is slightly trickier. If G prime has a flow of K, then G has a matching of size K. Right? So this is the other half. This is the other direction. We wanted to show if and only if. We showed if, and now only if. Okay. This is it's not so easy to see why this is true. Let me give you an example. Consider this graph right here. Okay, so this is a source, this is the sink. And now imagine we put flow like this. Okay, so this has flow of 1 unit, but how are we going to extract a matching? Because this node has like 1/2 unit of flow and this has 1/2 unit of flow. Do we round them up? Come up with a matching of 2? Right? So how do we deal with the fact that a flow, although the value of the flow is 1, it could actually be it would be easy if all the values were 1 or 0, right? Because then if the edge had a flow of 1, we could basically do the exact opposite of this argument. If there was a flow, if the edge had 1, then we put that edge in the matching. If it was 0, then we ignore that edge. And the problem is that some of these edges might have values like this. So when we encounter something like this, what should we try to do? Yeah?
Make them all integers.
Argue that it never happens, yes. And so therefore make them all integers. Very good. So here's what we want to argue. Here's how we're going to get out of this conundrum. We're going to say, if all of the capacities in a graph are integral, if the capacities on a graph are all integral, then the max flow will be integral, meaning that all of the flow values that you push across the network will be integers. Why is this true? Spend 2 minutes with your neighbor trying to convince them that this is true, trying to figure out why it's true. How you'd go about proving it. You got it? Okay, how's it work?
So if all the classes are integers, let's say like this is money, like that's okay. If it weren't filled up all the way, let's say you want to put up copper, then it would be mass flow, and all the sequential pipes that it's connected to also including copper. They're also
Well, what if, okay, so okay, consider that example. So this is a max flow. It has keep on discussing. I was just coming up with a counterexample for this. Right, so it has a max flow. All the constraints are satisfied, but the middle edges all have capacity half. No. This is actually the flow across that edge is a half. Well, let's say the capacity on every edge is also 1. Oh, you can't look up the answer. That's not fair. Oh, you guys figured it out? Yeah. So you do by induction. You say first it starts. You had another question you said? Yes, you can do that. Yeah. Yep. Mm-hmm. Yep. So as you'll see in the homework, there are lots of Idea? Okay, so where are you lost? You understand the question?
Yeah.
Okay. But how to argue it? That's where you lost? Yes, that's right. Size of a set. Flow, flow is defined. The value of a flow is essentially all of the material leaving the source. Because by all those other constraints, that means that's all the material coming into the sink. You can look at it. Okay, so you see it's a tricky problem. And a few of you have come to this kind of idea of how to actually show this is true. And the idea is like this. So if the capacities are all integral, consider what we know that Ford-Fulkerson computes a maximum flow, right? There could be many ways of computing maximal flows. Oh, I see. Sorry. Actually, I've said this theorem statement. Okay, so if all capacities are integral, there exists a max flow that will be integral. There could be many max flows for a particular problem, right? Just like in this case, this is a max flow that's not integral, even though all of the edge capacities are 1. But if all of the capacities are integral, then consider what Ford-Fulkerson does. Okay? At the start, the capacities and the flow are integral, right? What is the flow at the start? 0. And the capacities, by the hypothesis, are integral. Good. So now, suppose this is true for the first k iterations of the Ford-Fulkerson loop. Suppose that after k iterations, the capacities and the flow are both integral. On the next loop, augmenting path will have, what will be true of the augmenting path? We know that the capacities in the flow are currently all integral. Now Ford Fulkerson says find another path from source to sink. What can we say about this path?
Integral?
Integral. Its bottleneck edge will be an integer, right? So if the bottleneck edge is an integer, that means that the next residual graph, as you subtract that integer out from each of the integral capacities on the edge on the graph so far, this implies that the next residual graph will have integral capacities, right? Because this augmenting path had an integer as the bottleneck, that means when we push flow across that thing, the residual graph will just be adding integers or subtracting integers to values that are already integers, so those will all be integral. And also, the flow will be integral. Because if the bottleneck edge is an integer, the new flow will also be integral. Okay? So this is kind of like induction on Ford Fulkerson to show if the capacities were an integer, then there has to be some max flow that also has integral values. Question?
Yeah, so in the last slide, is this graph, is the capacity on all edges 1?
Yes? The bottom statement.
So then when we find a path from source to sink, wouldn't the critical edge be 1/2?
Oh, sorry. The way to interpret this graph, these values are all flows.
Oh, okay.
So one unit is flowing here, a half is going there, and a half is going there. One unit is flowing here, and a half is going here, and a half is going here. It's in order to mess up, it's to show that this theorem, you can't just apply this argument in reverse. Because all of the middle edges, none of the middle edges here have flow of 1 or 0. All of the middle edges right here have a fractional flow. Okay? So what we want to show is that G prime here has a flow of K. I'd like to show that therefore this graph G, the middle graph right here, right? The middle graph right here, I'd like to show that has a matching of size K. I can't do that with a simple argument because of this counterexample. Does everybody see that? Because how could I transform that into a matching? Every edge has some flow across it, so how can I select among all of those edges, how can I select a set where each edge touches at most 1?
Okay, you're saying that there's some max flow where we select integral critical edge.
Yes. So here's the argument I'm going to make the next step. I'm going to say, well, we have this integrality theorem. So that means if G has a flow of K, then that means step 2, there exists an integral flow right? So in other words, this argument needed one subtle addition, which is this integrality theorem, which is not obvious, but it has a simple argument. Okay? So we say if G has a flow of size K, that means that there's an integral flow with value K, and that means that since capacities then we know that the flow, since the flow is integral, and since capacities are 1, that means the flow on every edge in this integral flow is either going to be 0 or 1. Okay? And now, consider all middle edges so define M to basically be the set of all edges where the flow is equal to 1. I'm going to claim that the size of M is K, okay? So since the value of the flow is K, and each edge can either have 0 or 1, that means there has to be at least K edges, right? If the flow is K and each edge can only have 1, that means there have to be K edges. So this set has size K, check mark. Why is the set a matching? Why is this set a matching? Yeah? Well, this is what we'd like to show. Right? All we know at this point is that, all we can argue from this point is that we have an integral flow. And this is going to follow by properties of the flow. In particular, it's going to be the flow constraint. Okay, so we want to show that every edge here touches at most one vertex. Every edge touches at most one vertex. And so we selected this edge because there was one unit of flow leaving leaving X. Now by the flow constraint, there can only be one unit of flow coming into X, right? Because the way that we've constructed our graph, there's only one edge from S to X. If the outgoing flow is 1 unit, by the flow constraint, in other words, if 2 edges were to touch some value x, that means that the outgoing flow from that had to be 2. But by the flow constraint and the structure of the graph, the incoming flow could only be 1. So that would be a contradiction. Okay? What is the running time of this algorithm? Spend 2 minutes with your partner trying to argue the shortest running time for this algorithm. Everybody understand what we're doing? We construct this graph by adding an S and a T, and we run max flow on it. We know that the first and the last step take order E, so how much time does the middle step take? Yeah? You can do whatever you want. Yeah. Yep, you can say use Ford Fulkerson, you can use say Edmonds Karp, you can say use the integrality theorem that I just showed. You don't have to reprove any of that. But you would have to set up the argument the same way. You have to do an if and only if. So have you figured it out?
Multiply that with e squared plus EV squared plus 2 EV squared.
Okay. Can you argue that the running time is going to be order EV? So let's focus this slightly more. I want you to try to find an argument that the running time is going to be order EV. You guys got it?
It would only go the number.
Order EV. So if there's an over 2, it could be in the constant there. Yeah. It probably is like that. Depends. You can find some. Yeah. How come there are only that many augmenting paths? Let's say I had 100 nodes here and 100 nodes there, and this one touched each of these 100, and this one touched each of those 100. So it's a full graph, right? So 100 nodes, 100 edges each. So it's like 10,000 edges, right? So there could be 10,000 paths through this. In other words, there could be v squared. So if I started, v in this case would be like 100 plus 100, 200, right? Let's just call v 100. So there are v squared paths. So your argument would be ev squared. What do you mean?
Is it because something to do with
Yeah, an edge can only be critical, but how many edges are in this graph? They're v squared edges. Okay, so this is a cool little subtle analysis trick. Question?
When we say E, does that include the edges from the source to the left half and the right half?
Yes. Does that help out? So here's what I'm looking for. We often jump to Edmonds Karp because that's kind of the better algorithm, and that's going to run, Edmonds Karp would basically run in E squared V time, right? The trick here is to say, what is the maximum flow of this graph? We're actually going to use the Ford-Fulkerson analysis here. Right? So the max flow here has to be at most V. Okay? And so by the Ford-Fulkerson analysis, the running time is order E times F star, and so in this case, it's going to be order E times V. So in special graphs that you analyze, if you can upper bound the max flow by some reasonable constant, you can possibly get a running time that's better than our other analysis. In other words, right, we have different regimes call for different analysis. Edmonds-Karp is a generic algorithm, and it says upper bound is going to be E squared V. And in particular, right, since we're running the same algorithm, it's going to have the same running time here. The analysis just shows that it's going to actually finish in order EV time. Make sense? Okay, so a few more examples. Edge-disjoint paths. So when does this problem arise? The story that I sort of concocted last class was something like you're like a network, you're a Fortune 500 company, and you're basically doing your retreat from JFK to Fiji here, and you want to basically not have any two officers of your corporation flying along the same leg. Okay? So clearly you can get to Fiji from Charles de Gaulle. You can also get there from whatever, SFO and Hawaii. Okay. The point is, how can you find edge disjoint, all of the edge disjoint paths from JFK to Fiji? How are we going to solve this problem? So does everybody understand the problem? We want to find paths, like for example, here's one path. Okay, so here we found 4 routes. So the solution, yeah?
What were you trying to find again?
We're trying to find all edge disjoint paths from JFK to Fiji. Maximal number of edge disjoint paths. So in this case, you can only send your top 4 executives to Fiji. Yep.
You can set the capacities for each leg to 1 again.
That's it. That's it. Right there. All you got to do is make this the source, make this the sink, and set all of your capacities to 1. It's that cool. Okay? All you have to prove then, all you got to prove is that if G has K disjoint paths, then G prime has a flow with value K, and the opposite. If G prime has a flow I'd like you to think about how to prove both of these. They're going to be related to the previous ones. But just like the previous case, there's going to be a slightly... Cancel, right? Cancel, right? What if I just make it come over here?
Save option, save it. Cancel.
Cancel.
Okay. See, the people who said cancel are very trusting people. They're like, oh, the software's obviously cancel means make this thing go away, right? The people that are safe are like, you don't know who wrote this thing. Blind, oblivious, sloppy person wrote this thing. Cancel it has no semantics. You don't know what it's going to do. Save, on the other hand, they probably got that right. All right. Let's try to finish the rest of these examples. So here's another example. Now you actually want to be slightly more conservative. So these are your airports again. Oh, by the way, these edge disjoint paths, they can also be like in networking protocols, right? Suppose you want to do like a multicast. You want to send big chunks of data from here to Google, or you want to back up your hard drive and stuff. You want to find edge disjoint network paths in order to send all of your data, because there's no point in congesting one particular link. And so these type of situations are not just for Fortune 500 companies. They're for anybody who does backups online. Vertex disjoint paths. Suppose now the problem is modified such that not only do you want your executives to take separate flights, but you don't want any single one, since your executives don't really like each other, to be stuck at the same airport. So only one person can go through SFO, one person can go to London, one person can go through Detroit, and one person can go through Chicago, let's say. Okay? How can we solve this spend? Spend 3 minutes with your neighbor thinking about a way to solve the vertex disjoint paths. So the idea is you want to find the number of paths from the source to the sink in which all the paths are vertex disjoint. You can only use each vertex once. Hint, it's going to be related to the previous one. No. Clearly in practice you'd send them at different times, but then they would get there at different times. Here you just want to send from source to sink using paths that do not ever share a vertex. So take for example, see, take a look at these two purple paths. These are edge disjoint. These are edge disjoint paths, but they're not vertex disjoint. So we want to actually solve the vertex disjoint problem. Yeah.
When you can split what's the kind of trading type?
2, yeah. Every time you take a vertex and you make it into 2 vertices. Is that what you're thinking?
So then you can actually take the actual walk through the airport to get to the place. So you make the airport like
Exactly.
yeah.
I separated one point. I separated the G and H. Right.
Yes, exactly. It's exactly the thing he's saying. Okay, I've heard the solution about 3 times now, so it's filtering around. The idea is that you take each of these nodes, so for example, you take G here, and you transform it into a G in and a G out. Okay? And all of the nodes, all of the edges that were going into G, you change them into, you make them go into G in, and all of the edges that were going out of G, you make them come out of G out. So we're going to transform this graph. Every node in this graph, like G, is going to have a bunch of in edges and a bunch of out edges. We are going to take that node and transform it into 2 nodes, a G in and a G out. All the incomings come through here, all the outgoings go through there, and there's only one way to walk through the airport, as someone had made the analogy. Okay? Now we can take this problem and solve it using what? Edge disjoint paths. Because if there were two paths like this that run in SFO, then there would have to be two, basically, this constraint right here prevents the purple paths. Question in the back. That's true. So in this case, we would like to have, we want these to be directed edges. If there were the opposite, if there were edges in both directions, you'd treat them like that. Good question. Okay, pass it.
If there were edges in both directions, you would just make two separate edges.
Yeah, yeah. You're going to apply this process. Okay, very last, very cool application of this, which is not related to graphs at all. So take a look at this baseball elimination table. Clearly, Montreal has no chance here, right? They have 77 wins, only 3 games left, and Atlanta already has 83. So they're not going to any pennant. Agree? Okay, very good. Everybody understand what I just said here? Okay, so now let's consider this other situation. Can Detroit win or tie? Well, let's see. They look like they're not doing so well so far, but let's imagine they win every single game that's left. How many would that be? 76. Okay? So, and of course, New York has 75. Let's assume that, that means that New York can only win at most 1. Let's assume they lose everything else here. But within their own bracket right here, these are the number of games that are left. So New York has to play Baltimore, Boston, Toronto, and Detroit. Of course, the Detroit games, they're all going to lose because Detroit wins all of the remaining games, right? And let's see. The Baltimore games, of course, they lose those as well. But that means Baltimore won those 3. And so now Baltimore would have 74 wins at that situation. Boston had 8 games against New York, and if they lose all of these 8 games, that means Boston would have what? 77, which means Detroit can't win. So clearly, New York has to win at least 1 of these games, and Boston has to win 7 of them. So at this situation, we're at 76, and here we're also at 76, right? And now Toronto, yeah, okay, so they're going to lose all of these games, and Toronto will be at 7. But unfortunately, now when we go back to this situation with, New York and Boston, right? This was a 7-1 series, but what about Baltimore? Boston and Baltimore have 2 games, okay? And Baltimore currently has 74. That means Boston has to lose both of these games, right? Which means Baltimore would have 76 and 76. Now let's go back to Toronto. Okay? Toronto had 7 games with New York, which it won all of those, right? It was a 7-0. But now they still have 7 games left with Baltimore. Okay? And unfortunately, if they won 7 of those games, Toronto would have 77. So they can only win 6 of those games. But now all of a sudden, that means Baltimore has 77. So I just made a very crazy argument like, if this happens and that happens, and if this happens and that happens, and then if this happens and that happens, and if this happens and that happens, and if this happens and that happens, then Detroit is going to lose. Okay? But this was a kind of complicated argument. It involved a lot of if this, then that, if this and that, if this and that. Here is a more clever argument to make. Okay, let's see if I have a clean version of this. I don't. Okay. Okay. It's basically an averaging argument. Okay? So Detroit is going to have 76 games. 76 wins, definitely. Okay? And that means we take out all of these games because we've assumed that they've won them. Let's consider all of these right here. Let's add them all up. So 75 plus 71 plus 69 plus 63. And let's also add up all of the games that these teams have amongst each other. Okay? So it's going to be 3 plus 8 plus, so that's 10, 27, right? So this is how many wins they have, and somebody has to win these games. Let's assume that there are no ties in baseball, so of course they all won. What's the sum of these 5 numbers? What? 10, 25, 14, 20, 305. There are 305 wins that are divided among 4 teams. So the average has to be 76.25. Since wins are integral, that means some team must win 77. Isn't that a cleaner argument? I'm going to say among these 4 teams and the games left, they have to be 305 wins divided by 4 teams, which means some team has to have 77. Much better than if okay? The question is, how can you find such arguments, especially if these things are not just 5 teams, but let's say 15 teams or n teams? And the solution is max flow min cut. Okay, what we're going to do is transform the graph into something like this. We're going to put all the rivalries, like New York versus Baltimore, New York versus Boston, etc., all of these things on the left, all of the teams that accept the wins on the right. Here's the source, and here's the sink. Okay, here is how we're going to put these edges. So if New York wins 1, or Baltimore wins 5, or Boston wins 6, or Toronto wins 13, if any of these things happen, if that's the maximum that happens, then Detroit wins, because everybody else is 76 and this is a tie. So we basically put the number of games that are left on the left over here, and since this is a game that has to go between New York and Baltimore, and so the win is either going to be to New York or Baltimore. Okay, these are the games that are left. These are the games. These are how the wins have to be distributed so that Detroit still wins. And we're going to run a max flow min cut on this particular graph. And if it's possible, if the flow on this graph is larger, what do I want to say? The flow is either going to be this value right here, the sum of these games, or this value right here. And whichever one is the smaller one tells you whether the wins can be distributed in a way that lets Detroit win versus if they have to be distributed in some way so in other words, if the min cut of this graph is this right here, then Detroit loses. If the min cut is here, then there's a way for Detroit to win. Moreover, the actual value of that cut tells you if Detroit is going to lose, like in this case right here, the min cut will actually give you the set of teams for which you can run that averaging argument. Okay, I gotta let you guys go, but please come ask me some few questions right after this. What are the infinity?